So in this video, I'm going to talk about normal distribution, normal random variable, one of very popular continuous random variable. So here is the density function of normal random variable. By the way, you need sigma here. So it's 1 over the square root 2 pi times sigma time e to the power negative 1/2 times x minus mu over sigma square. So let me write this more clearly. So since there's a small typo there, so it should be sigma times square root 2 pi, then e to the power negative 1/2 x minus mu over sigma square. One thing you can notice that x is defined over all real numbers. So, for example, exponential is defined over all non-negative real numbers. So in this case, it is defined over all real numbers. X is called as normal random variable with parameter mu and sigma. By the way, you can make this standardized. So this is just normal random variable with parameter mu and sigma. By setting mu equal to 0 and sigma equal to 1, you get standard normal random variable. For that one, we use the notation Z. So this is going to be 1 over square root 2 pi e to the power negative 1/2, then x minus, so sigma is 1, mu is 0, so this becomes C square. So if you see that formulation, then basically that's standardized normal random variable density function for that. So here you can see some properties. Expected value of normal random variable is mu. So these are two parameters. Like for example, exponential, we need to give only one parameter, either lambda or beta, depending on what you prefer. For this particular one, you need to give two parameters, mu and sigma. By the way, the shape of the density curve, you have seen this for sure. It's look like this, and here is the mu. The sigma basically measure the variance of the this random variable. So here I have several this homogeneity function. If you don't know about that, you can leave it as it is. The last one says if x and y are independent normal random variable with parameter mu and sigma, mu x and sigma x, mu y and sigma y, then x plus y is normal with parameter mu x, mu y, and the variance is sigma x square plus sigma y square. So that's a very useful property to know. So you need this condition, independent normal random variables. If x and y are just normal, adding x plus y is not going to be normal. There are counterexamples for that. You can search online and you can find it. But if x and y are independent normal random variables, then we have this property. So here we are going to we are trying to define central limit theorem actually. So let's go through this slide and then we go to central limit theorem. So suppose x is a random variable with finite mean mu and variance sigma x square. And if we add n copies of independent and identical distributed, so usually you see the IID, independent identical distributed, these random variables, and then if we say S is sum of that and x bar is average of that, then we have these two results. So S is you are summing up all are normal random variables with xi with mean mu and variance sigma. So the question is, what is extra value of S? Since n is fixed, it's going to be n time mu x. You can see you are basically adding the extra value of each one, and then the variance is going to be basically n time sigma x square. Since they are independent, you are just adding the copies of those variance from each. And then if you take the x bar, which is defined as x1 plus all the way up to xn divided by n, of course, this is going to be, so n to n cancel out. You can see this because this is going to be now, this is basically s divided by n. So So expected value of x bar is going to be n time mu x divided by n, which is mu x. And the variance of x bar is going to be variance of s divided by n square, because when you take the variance of everything, 1 over n become n square. So variance of s is n sigma x square divided by n square, and you have sigma x square divided by n. And when you take the this should be sigma x square divided by n, not square root of n. And then when you take the standard deviation, it becomes square root of n. So central limit theorem says let x be a population random variable with finite mean mu x and finite variance sigma x square. Let s equal sigma equal 1 to n xi, then for large sample size to n, the distribution of s is approximately normal, with mu is n mu x and variance is n sigma x square. And actually the second part is x bar. If you take the average, it's normal distributed with mean mu x and the variance sigma x square divided by n. So that's the second part of that. Sometimes you can use normal sometimes you can use normal distribution to approximate binomial distribution. By the way, the binomial distribution is discrete. So when you have when you want to approximate binomial distribution, you need to do the continuous correction. For example, how do you calculate probability x equals c if x is binomial using normal approximation? So in order to do that, you have to use this continuous correction. So for example, if probability x less than c, that would be in normal. So this is for binomial. Then in order to get that, we will add 0.5 to that. So this is probably x less than c plus 0.5. This is after the continuous correction, and using normal distribution. Let's do a few examples and see how to do this, how to use these distributions. So here you can see first problem, and it says the minimum force required to break a particular type of cable is normally distributed with mean given and standard deviation. A random sample 400 cables of this type is selected. Calculate the probability that at least 1049 of selected cable will not break under force of 12,400. So so what's the probability that it will break? So basically, let's say y. Y is the probability that the probability that cables will not break under force of 12,400. So this is the so y is minimum force. Let's define y is minimum force required to break a cable. So what's the probability that it will not break under this one? So we want to know this one. So y is normal distributed with mean 12,432 and sigma equal 25. So this one I can calculate probability y minus 12,000. By the way, so when you are doing this kind of problem in exam setting, you have to standardize this. So that give you probability y minus mu over sigma. So mu is 12,432, sigma is 25. So this is probability C more than this number is going to be, let's see, 12,400 minus 12,432 and divide by 25, we get negative 1.8. So we want to know the probability, and what we can do, we can use SOA calculator. So if I use SOA calculator, so so I want to find the C more than X. So let's type. So this is so less than X, that's 0.10. So more than that is, let me go back to the. So here we will get more than that. So if I calculate probability C less than negative 1.28, I got around 0.1. So more than, that's going to be 0.9. So that's the minimum force required to break the cable. I mean, the minimum force required to break the, not to break under the force of 12. So what's the probability of that? That's 0.9. So now we have sample of 400. And the probability of each one breaking is, I mean, the failure is, success is 0.9, not breaking is 0.9. And we want to know if we take the random sample, n is more than 349. So n is number of cables which will not break under force of 12,400. So what we so basically n is going to be binomial because you have only two possibilities, either it break or not break. So the binomial with probability of 0.9 for success, not breaking, and then the number of trials, n is 400. So this is P. So we need two parameters for binomial, NP and P. So this implies probability n more than 349. So basically, if you know the binomial distribution, the way you calculate this, you start calculating this way: 350, 351, and so forth, all the way up to 400. So every time you apply the binomial probability formula, but you can see this is not going to be easy. So what we can do, we can do the continuous, we can use the continuous distribution to approximate that. So what we are going to use normal. So if we use normal distribution, then so we need to extract mean and sigma from this binomial distribution. So basically mu is going to be NP, sigma is NPQ. And then we are going to use that in approximating that probability using normal distribution. So n times P is 400 times 0.9. And this one is 400 times 0.9 times 0.1. So you get, this one is 360. And sigma is basically square root of NPQ. That's going to be 6. So now I can come back, and so now I'm using normal distribution. Okay, so approximate with normal distribution. So probability n more than 349. But remember that we have to do some continuity correction. So if I go back here in this table, x is more than c is same as x is more than c minus 0.5. So this is probability n more than 348.5. And then now I can make it standard minus mu over sigma. So that would be probability z. This is standard one now. 348.5 minus 360 divided by 6. And when you use your calculator, you will get 0.97. So first we calculate the probability of given cable not breaking under force of 12,400. So y is minimum force required break cable. So this means basically this probability, because it's more than 12,400, y is basically this means cable is not going to break. That's the probability for that. So that's the probability is 0.9. Then what we did, we had a cable of 400 and we want to know what's the probability that 349 cable break. So n is basically number of cables not break, did not break. So basically you take, it's a binomial, either break or not break. So success is not breaking, which is probability of 0.9 when you apply force of 12,400 and you have 400 of those cables. So the average number for number of cables not breaking is n time p, which is 360. Standard deviation is you take n time p time q, which is 6. So you want to know what's the probability is more than 349. If you apply binomial right away, you have to add all of these, which is going to be really tedious. So what you do, you do the approximation using normal distribution. In order to do approximation, you have to do the continuity correction, and then after that you can apply the normal distribution with the mu coming from here, binomial, sigma coming from binomial, and then using normal distribution, calculate the probability. Okay, so here's another example. In this example, it says Abby's mother scored at 93rd percentile in the math stats exam. So let's see what's Abby's mother score. So let's see. This is y, and then the probability y. Let's say the SAT score is y, and Abby's mother score is some particular number. Okay, so y is 1982. SAT score, and A is Abby's mother score. So probability y less than or equal A is basically 0.93. So probability y minus mean was 503. Variance is that one, so we have to take the square root in order to get the standard deviation. So that means we have to take the 93rd percentile for that particular distribution. So now we can use a standard deviation because standard normal random variable because we standardize this. So that means this one should be equal to 93rd percentile. So if I use my the calculator, so this side we need 0.93. 0.93. So it's 1.47579. 1.47579. So So this one should be equal to 1.47579. From here, I can get A. So so A becomes 647.619. So then in 2008, Abby took the math stat score and got the same numerical score. So this is same as also Abby. So that's Abby's score too. So Abby's mother score and Abby's score both are same, which is 647.619. And then now, but the now mean and variance are different. So we want to get the percentile. Um, so So you want to know y less than or equal 647.619. What's that number? The percentile. So we standardize again, but with different mean and standard deviation. No problem. So this is now standard. So we have this become 1.250366. And then if I use my prometric calculator, so we have x 1.2536, and the probability is 0.89506. So then this become so this imply P equal 0.89501. So basically 90% time, because it's more than 89%. So in this one, it says certain brand of refrigerator has a useful life that is normally suited with mean 10 years and standard deviation of 3 years. So if X is the life, it's normal distributed with mu equal 10 and sigma equal 3. The useful lives of this refrigerator are independent. So that's very important. Calculate the probability that total useful life of two random selected refrigerator is 1.9 times useful life of third random source. So we have 3, 1, x, y, z. So we want to know the probability. X plus y is more than 1.9 times z. So this one would give us, so if I bring everything into one side, so what's the probability of that? Remember that when you add normal random variable, if they are independent, then they are going to be normal. So expected value of x plus y minus 1.9 c. So this is basically, let's say, some new random value, let's say it's a. This is going to be normal. My question, so before that, I need to know the mu and sigma for that new one. So if I add this, you can see this is going to be Ex plus Ey, since they are independent, minus 1.9 times Ec, which is 10 plus 10 minus 1.9 times 10. So that's going to be 1. And then I need the variance of x plus y minus 1.9 c. They are normal because they are independent, but variance, when you add in this, negative sign become squared. So it's going to be, they are independent, so I can add it. But here I'll have 1.9 square time variance of C. So 3 plus 3 square plus 3 square plus 1.9 square time 3 square. So that gave me 50.49. So now now let's calculate the probability. So probability A is being positive. That's probability A minus mu, that is 1 divided by square root of 50.49. 0.1 divided by square root of 50.49. That's that probability. So that's the probability C is more than negative 0.140733. So that probability, if I use calculator, zero point one four 140723. Probability is 0.5596. So the probability is 0.5596. Since we use calculator, actually that the time when they wrote this one, they had table. So I think it should be 0.556 because the table values are not close like the ones we are using right now, calculator from the geometry. So I'm going to skip the remaining problems. You can try and then let me know how it goes. If you need my help, let me know. The next distribution we are going to define, actually we are not going to do any problems, but define the log normal distribution, gamma and beta distributions. The log normal distribution is defined as follows. If X is normal random variable with parameter mu and sigma, then Y equal e to the X is said to have log normal distribution with parameter mu and sigma. So in other words, Y is log normal if log Y is normal. Okay, so Y is log normal if and only if log Y is normal. So here you can see a few properties of log normal distribution. X value of Y is going to be this value, and we are not going to prove that. You can either memorize it. I mean, actually, that's the only possibility. For the exam, you can memorize it because if you try to derive it, it may take more time. And this is a kth moment, how that ones look like. And then you can see the CDF and PDF. I don't think you need the PDF function, but the CDF function you can see this one is actually easy to derive. So if you want probability, Y is less than Y, then this is same as taking log both side. And then log Y is normal, so that's same as so that means basically same as taking the normal distribution. So this is normal. This is normal CDF. So that's why you have log Y, mu, and sigma. But the other XP value variance and kth moment, I suggest you to memorize it. So here, two other continuous distribution, gamma and beta. The gamma function is defined using this integral. So here you can see a few properties. Gamma alpha equal alpha minus 1 times gamma alpha minus 1. Gamma n is n minus 1 factorial, gamma 1 half square root of 5. So this gamma function, then based on that, you can define gamma distribution. You can see gamma distribution is defined using this um, use as this one. One thing to note is that it's defined over positive real numbers. And it has two parameters, alpha and lambda. And the expert value is alpha over lambda, variance is alpha over lambda square. By the way, this kind of, you will learn more about this distribution when you take the STM exams. But right now, more like you can identify the shape and then easily extract the expert value and variance. So if you see a density function and you can kind of like match it to the gamma distribution, and if you can extract basically alpha and lambda, then you can easily get expert value and variance. So that would be your task as of now, extracting those things. So here is the similar to exponential distribution, you have different parameterization where you can define lambda as 1 over lambda as theta, and then you will have different. If you do that way, then the EX become alpha theta, this one become alpha theta square. So gamma, when you have alpha equal 1, we get exponential distribution from this one. And when alpha equal n, we get distribution of sum of n independent exponential random variable. When alpha equal 1 half and lambda equal n over 2, we get chi-square distribution. Similarly, we can define another distribution, which is called as beta. Plus, we define beta function. Here you can see the beta function and some properties. And then the beta distribution is defined here. So again, when you see a distribution, if you can match the format to that distribution, and then you can easily get the expert value and variance. If you remember this, you don't have to do the you don't have to worry about what's expert value, because basically the question would be like, you have a density function, somehow you need to get expert value. If you remember the format, then you can extract, use the formula, just extract A and B and then apply the formula. So that would be the end of this module.